Okay, so in this problem, there's this discussion of a magnet. We have a magnetic field. Conveniently, by the way, the magnetic field is approximately uniform. We're going to treat the magnetic field as being uniform. So it's the same no matter where you are. And you can see that from the formula for B. There's no X, Y, or Z in the formula for B. Now it changes with time. Different values of T, different magnetic field, but it's approximately constant wherever you are spatially. Okay, and so we've got a magnetic field that's changing, and we are interested in the line integral of the electric field. So where, oh where, have we seen that before? And here you go, line integral of the electric field. Right? And what we see is that it depends, well, conveniently for this problem, on how magnetic flux is changing. Well, we know how the magnetic field is changing. So we just have to see how is the magnetic flux changing. Does that make sense? So this is the big equation that we're going to use in this problem. And let's write that down. So line integral around the boundary of a surface there, E dot dx, is the negative time derivative of the magnetic flux. Okay, now back to the problem. Oops. Okay. All right, so let's look at our situation. We have a wire. Okay, the wire is in the shape of a unit circle in the XY plane. So it's kind of like that. There's our wire. And that wire, of course, is indeed the boundary of this surface S that I'm going to make just the unit disk in the XY plane because that's convenient. Everybody good? Okay. All right. So the problem asks for the line integral of the electric field in a counterclockwise direction around the wire. Now, shame on me, I didn't say as seen from which direction. Presumably I meant counterclockwise as seen from above. So let's say we're going this way around the wire. Well, that curve, counterclockwise around that circle, that is the boundary of the upward-oriented surface S. So that means that the line integral in question, line integral of the electric field around the boundary of that surface, is the negative time derivative of the magnetic flux. So I'm just going to compute the magnetic flux, take the time derivative of it, and multiply by a minus sign. Does that make sense? You see how this Maxwell's law is helping us out? Okay. All right. Okay, so magnetic flux, well, let's see here. What's the magnetic flux? Magnetic flux is flux integral B dot ds. Well, let's see here. I can actually just write that down. Well, let me rewrite this a little bit. I'll call B dot little n ds scalar. Now, alternatively, you could parameterize this surface. It'd be fine, right? And compute, B dot capital N du dv or something like that. But I think the geometry is convenient enough that this is going to work out nicely. Okay. So where's our magnetic field? Well, there it is. It's given. It's 3 minus t, 4 plus 2t, 2 plus 5t, okay, what's our unit normal vector? Well, that's easy. There it is. We were clever enough to choose the nice flat surface there whose boundary is this curve in question, and that normal vector is just 0, 0, 1. Right? And then ds scalar. Dot product is easy to calculate. So I have 2 plus 5t ds. Now you do have a double integral to calculate here. I'm going to show you a trick for how to calculate this. but you could just, chapter 5, brute force this. But there's a clever way. I like the clever, right? Excuse me. I'm sorry. I misinterpreted my own writing. No, this actually is pretty easy to calculate because this is a constant, right? It depends on t, but as far as the integral is concerned, the integral is over this surface, and for any given value of t, it's the same no matter where you are in the surface, no matter what x and y are. 2 plus 5t is always the same. So you can rewrite this as 2 plus 5t times, and then just the surface area of that surface. Well, that's a unit circle, if I remember correctly. Yeah, unit circle area is pi. So I just have 2 pi plus 5 pi t. That's our magnetic flux. Everybody good so far? So the way we wrap this up is the line integral that we're interested in is the negative time derivative of that. So I have negative d by dt of 2 pi plus 5 pi t, and that is, let's see, negative 5 pi. That's a 5. Yeah. Make sense to everybody? Everybody happy? Okay.